All right, so thank you so much for joining. This is session 6. That is a continuation of where we left off from. And today we are continuing probability distributions, but we are going to have a focus on the concept of normal distribution. And the last time we met, we looked at some discrete probability distributions. We looked at the binomial distribution, we looked at the Poisson distribution, and we also touched on the hypergeometric distribution. This week, we want to look at the normal distribution, the normal distribution. So there, that's it. So most phenomena in life are modeled using the normal distribution. And the normal distribution is like, I call it the mother of all distributions. Okay. And when we begin to look at statistical tests, which we are going to do, hypothesis testing, analysis of variance, and then simple linear regression, we will see the role that normal distribution plays in these situations. So normal distribution is quite a big deal as far as probability distributions are concerned. And at the end of this session, I believe that you should be able to understand what the normal distribution is, how different is the normal distribution from the standard normal distribution, and how do we standardize, okay, and go into a process called standardization. How do we calculate probabilities from a standard normal distribution using the normal distribution tables? Okay, so this is your reading list, and I hope you've been reading. Okay, yeah, as I said. Yeah. So the normal distribution, what at all is the normal distribution? How do we describe the normal distribution? Now, the normal distribution is characterized by a bell-shaped curve. Okay, a bell-shaped curve, and it's symmetrical. This is what we call a bell-shaped curve. If you can see this as based on what I'm pointing, this is what we call a bell-shaped curve. You see, it's shaped like a bell, and it's symmetrical. When we say symmetrical, you see, the characteristics at the left, the one half of the curve has the same as the characteristic that appears on the other half of the curve. And then we have the mean, the median, and then the mode being the same. Mostly we call the mean the location parameter. Okay, the location parameter. So it gives you the direction or the location of the standard, no, sorry, of the normal distribution curve, the center of the normal distribution curve, and then the spread, how wide this curve is also determined by the standard deviation. Now, for any normally distributed random variable, the variables, the values range from negative infinity up to positive infinity. And normal distribution, as we said, has a lot of most of the phenomena in life can be modeled using the normal distribution. Okay, and it just tells you that in a very crude way or in a layman's way of explaining, it highlights the phenomenon where most of the people or most of the frequent majority of the population or sample are centered in the middle, and then a few are at the edges. Okay, so if you take a typical examination, okay, if you take a typical examination score, okay, you have something like this, okay, and what this is showing basically is that you have a lot of people scoring the 50s and then the 60s. You know, the average students, most of them will be concentrated here. Then we have a few people scoring the 20s and then the 30s, and then yeah, trying as much as possible to fail. And then we also have quite a few people also scoring the 80s and the 90s and the 100s. So we have a lot of people clustered in the middle, okay, in the middle, and then we have a few people clustered at the edges. Um, if we have a poverty or a standard of living distribution where we have a lot of people being at the middle point, as in living average lifestyles. And then you have so many people, a few people who are very, very poor, and then a few people who are very, very rich, like filthy rich. Okay, then this can be the normal distribution. If you take shoe sizes, for instance, let's take the typical size of a lady's shoe. Can someone help me? What's the average size of a lady's shoe? A lady's slippers or sandals or something like that. What's the average size? Anybody to help? 39. Okay, very good. Good. Wow, 40. Okay. So let's say that the average lady shoe size is 39. So 39 is somewhere here in the middle. So you see that a lot of ladies will be wearing shoes with sizes 38, 37, 39, and say 40, clustered in the middle. Then we have a few people who would be wearing 32, 31, very, very small legs, right? 33, and so on and so forth. And then we have quite another fewer wearing 43, 44, 45. That means that the person is inching towards masculinity, right? So those are some of the situations we find ourselves in using average stuff like that. Okay, and those things can be modeled as a normal distribution and a normally distributed random variable. So if it is not symmetric, okay, if it is not symmetric, then it means that the distribution is what we call a skewed distribution. If it's not symmetric, then it is skewed. Okay. If it's not symmetric, then it is skewed. We say skewed. And then the distribution can be skewed either to the left or to the right. We can either have a skewed distribution to the left or to the right. So let's take an example. Now imagine you have an examination where a lot of students did well. Okay, a lot of students did well. Then it means that you have something like this. Let's say that is the line. Sorry about that. And then it moves here, and then it picks up something like this, right? Now, this skewed distribution helps you to know that a lot of people are on the large high scores end, right? So let's say maybe some questions got leaked and people got access to the questions, and so they perform so well, or probably people really took the course seriously and prepared adequately for it. So the people actually did well in that sense, right? And assuming that so that means that this is a skewed distribution. Now, because this is skewed distribution, this is not symmetric, right? And the tail of the distribution is pointing towards the left side. So we call this a negatively skewed distribution. Negatively skewed distribution. Then we have the reverse, okay, where so many people didn't do well, right? Maybe the questions that leaked, the authorities found out that the questions had leaked and quickly changed the questions, right? And when they did that, and people didn't realize that the questions have been changed. So when they went, the whatever they had studied had good swerved them, or maybe people didn't really prepare adequately for the paper. So you have a lot of people failing, a lot of people not doing so well. So you see that this is actually skewed to the left, and then the tail of the distribution is pointing towards the right. So we call this kind of distribution, and a positively skewed distribution. This one is a negatively skewed distribution, and this part is what we are terming as a positively skewed distribution. And then when it is few perform extremely better, few perform extremely poorly, a lot of people are around the middle, then we call it a symmetric distribution. Okay, so these are some of the things that you should take note of as we move on. All right, thank you. So basically, that is what we have as far as normal distribution is concerned. Now, the mean is found in the middle of the distribution. Okay, so as you can see, the mean is the center, and then the spread is determined by the standard deviation. The spread is determined by the standard deviation. So anytime you decide to change the value of the mean, okay, anytime you decide to change the value of the mean, then it feels like you are shifting the curve from one location to another. Literally, you are carrying the normal distribution curve from one point to another, okay, without expanding it or without contracting it. Okay, so if you change the mu or you change the value of the mean, you either shift the distribution left or right. Okay, but if we change the standard deviation, okay, then it means that we are either widening the curve or we are contracting it. So either we increase the spread or we reduce the spread. Basically, that is what we are talking about. Okay, so someone is asking which one is the negatively skewed and which one is the positively skewed. I said the first one here is the negatively skewed distribution, and that is measuring the situation where you have so many people or so many a majority of the sample of population having the higher frequency, having the higher score, and then a fewer having lower scores. I know there's that confusion about if it is positively skewed, then you should, I mean, more people should be doing well, so that's positive. Don't think about it that way. Look at the direction of the tail of this distribution, and this tail is pointing towards the left, so that's why we call it a negatively skewed distribution, and the reverse is what we are terming as a positively skewed distribution. So many people are not doing so well, and we have a lot of people performing, a few people performing quite remarkably. And so the tail of the distribution is pointing towards the right. That's why we are calling this a positively skewed distribution. I hope that your results in 301 would either be symmetric or negatively skewed, right? We don't want positively skewed distributions ever in our classes or in our results. All right, thank you. Okay, so as I was saying, if you change the mean, okay, you either shift the distribution to the left or to the right. It's like you are literally carrying the distribution or the curve from one point to the other. But if you shift the standard deviation, it's like you are maintaining the position of the curve of the diagram, but you are just widening the curve or you are contrasting it. I think there's an example in the next slide that speaks to it. So if you look at these three graphs, okay, the yellow one, the green one, and then the purple one. Now the yellow, okay, and then the green have the same mean. You see that they have the same mean, but the purple one has a different mean. You realize that. But although the yellow and the green have the same mean, they have different standard deviations because one is one is wider than the other. Okay, the purple one is wider in terms of its spread and it's also different in terms of its direction. So that one also has a different standard deviation and also has a different mean. Okay, so If I literally lift this green one, okay, I lift it from where it is now without contrasting it or without enlarging it or without increasing the spread. I lift it from one point and I put it at another. Then it means that I've just changed the location. In other words, I've just changed the mean or I've varied the mean, but I haven't changed anything about it in terms of the standard deviation. Okay, how do we measure probabilities using the normal distribution? We measure the probability based on the area under the normal distribution curve. Those of you who are familiar with integration, right? And we are not going to do integration, so don't worry. I'm just illustrating something. Those of you who are familiar with integration, when we're doing integration, we indicated that if you want to find the area under a certain curve or area under a certain plane, it is when you integrate over a certain limit, right? A lower limit and then an upper limit. That will give you the area of the curve. It's the same idea that we are having here. Okay, so if I want to find the probability that a number is ranging between, or a variable ranges between two values and is normally distributed, then it means that you are just going to find the area that is under the two limits. Okay, so if I want to find the probability that x lies between A and B, then it means that I'm just finding the area that is under the curve with the limits A and B being the lower and then the upper limits respectively. So because this is a symmetric distribution, the mean actually divides the normal distribution into two equal halves. Okay, the mean divides the normal distribution into two equal halves. So one half of the distribution has an area of zero point 0.5. The other half of the distribution has an area of zero point 0.5. And when you put these two together, the entire area occupied under the curve is 1. Okay, because you would know that the total probability for a mutually exclusive and an exhaustive event, right? Or situation of that nature gives a probability of 1. That's the total probability rule. So in this case, the total area under this curve, okay, is 1, and because it is symmetric, it is half above the mean and is also half below the mean. So from negative infinity up till the mean, okay, is zero point 0.5, and then from positive infinity, from the mean up to positive infinity is also zero point 0.5. So if you evaluate negative infinity to positive infinity, then you obtain a probability of 1. I hope that is okay. All right. Now, how do we understand about all of these things? What can we say about these situations now? And I wanted to pay attention here, especially what I'm coming to say. Now, the normal distribution, as I mentioned, is such that we have majority of the sample or majority of the population um, clustering at the center of the distribution, as you can see from here. Okay, so we have a lot of people in this situation. Now, if you move one standard deviation to the left of the mean, and then you move one standard deviation to the right of the mean. Okay, that boundary, this point, you realize that I have I have moved one standard deviation to the left of the mean, and I've also moved one standard deviation to the right of the mean. The area that is occupied under such a curve, okay, under this normal curve between this point, this lower limit and that upper limit is mostly about 68.26%. Okay, this is something that has been proven. Okay, so we know that if you move one standard deviation to the left and then one standard deviation to the right, the area occupied under that curve, under the normal curve, given that information, is about 68.26%. Okay, so it contains roughly about 68.26% of the data that we have. Now, if you move two standard deviations to the left and then two standard deviations to the right, then it means that you are occupying a larger area. Okay, and given such an information, you are basically having about 95% of the data lying two standard deviations to the left and then two standard deviations to the right of the mean. So the idea is that given such a limit, this lower limit and upper limit, the area occupied under this limit is about 95.44%. And this has also been proven. If we extend, that means you are covering more and more of the data, right? So if we move three standard deviations to the left and then three standard deviations to the right, then it means that we are occupying about 99.72% of the data. So the more we move, the more standard deviations we move towards the left and then towards the right of the mean, the more we capture the data and then the information under the curve. Okay, so that is it about the normal distribution. Okay, so and the more standard deviations it is from the mean, okay, with a normal distribution, the further away it is from the mean. Okay, the more standard deviations it is, the further away it is. So the question really is, how do we calculate probabilities given this given the things that we have? We have a very interesting relation that we are going to use, and as you can see, the probability of x for a normal distribution is given as this: 1 over sigma square root of 2 pi e, the exponents, x minus mu squared divided by 2 sigma squared. And if we want to, because this is a continuous random variable, okay, because this is a continuous random variable, if you are finding probabilities that is located within an interval, unlike the discrete random variable where we were adding the probabilities. For the continuous random variable, we cannot just add the probabilities, okay, and we have to integrate over the area. Okay, let's take for example, let's take for example. So okay, let me just clear all of these things that we have. All right, so let's take for example. Okay, so we clean up all the mess that we've created. Okay, very good. So let's say that you know, when I had a typical binomial distribution, I was supposed to find the probability that, let's say, x is equal to x is less or um, s is less than or equal to, say, 4, right? We indicated that this was the same as the probability that x is equal to 1. Sorry, from the x equal to 0 plus the probability probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3 plus the probability that x is equal to 4, right? So we had something like this. You find the individual probabilities and then you add them. This is true for a discrete random variable, okay? But for a continuous random variable, this cannot hold. The reason being that if I'm supposed to find probably that x is less or equal to 4 for a continuous random variable, okay, I know probably the thing is ranging from 0 to 4, right? But between 0 and 1, there are millions and millions of numbers that are hiding in between 0 and 1. Okay, because it's a continuous distribution and it can take over all the numbers. It can take every numbers in the real line. Okay. Oh, it's less than or equal to. Sorry. Thanks. So we have that. All right. Thanks. So we can assume any number in the real line. So if you are just adding 1, 2, 3, and 4, or 0, 1, 2, 3, and 4, you are missing so many points that should be considered as far as the continuous distribution is concerned. Okay, so we cannot just add; we have to integrate over the limits. Okay, so here would have been the integral, right? So here would have been the integral from, let's say, 0 and then to 4, and then we put in the formula of the distribution. That's the distribution, the probability function. Okay, so we would have put in this, and then we would solve, and then we would find the answer. Yeah. So in other words, the mu is the mean, as you already know. The sigma is the standard deviation. We have pi, and then we have e going to be 2.73. Okay. All right. Now there is a special kind of distribution. Okay. There's a special kind of normal distribution that has a mean of 0 and a standard deviation of 1. That distribution is what we term as the standard normal distribution. Okay, so the standard normal distribution is a distribution, of course, it's a normal distribution, but it is a normal distribution that has a mean of 0 and then a standard deviation of 1. So if you can see from this curve or from this example figure here, you see that the mean here is 0 and the spread here is 1. So you have a mean of 0 and then a standard deviation of 1. That represents a standard normal distribution. And standard normal distribution is very important as far as the determination of probabilities are concerned, and you will see that as we move ahead. Okay, any normal distribution that has a mean mu, okay, and then a standard deviation sigma can be converted into a standard normal distribution so that we can have a mean of 0 and then a standard deviation of 1. Okay, when that is done, that distribution becomes a standard normal distribution. And the process of doing such a conversion is what we term as standardization. If you were in class, I would have asked you to all repeat after me standardization. So wherever you are, repeat after me standardization. Very good. So any normal distribution that has a mean mu and a standard deviation sigma can be transformed into a standard normal distribution. Okay, and the process of doing that is what we are terming as the standardization. That it means that if you want to translate from any normal distribution x to the standard normal, and the moment we do that, that means that the probability or the variable x, okay, has not been transformed to a certain standard variable z. Okay, so that is to translate from any normal x to the standard normal, that is the z distribution. Okay, we have to undergo a certain process. First of all, you just have to subtract the x value, you have to subtract the mean from the x and then divide by the standard deviation. So standardizing is a very simple process, and we just have to do x minus mu divided by sigma, and this would convert your distribution into a standard normal distribution. Let's take an example. If x is normally distributed with a mean of 100, right, and a standard deviation of 50, okay, and I want to find the z value or the standardized score that corresponds to an x value of say 250, okay, how do we navigate that? So we know that our z is what, x minus mu divided by sigma, isn't it? So given that the value of x is what, is 250, the value of the mu is 100, and the standard deviation is what, 50. So we have 3.0. Okay. Now the standardization actually also helps you to identify how many standard deviations is x far away from the mean, right? So if I had a standard deviation, a standard normal distribution that had a mean of 100 and then a standard deviation of 50, right? And I'm looking for the probability or the z value that corresponds to the position of x equal to 250 with reference to the mean, right? If I standardize, I get 3.0. That means that x equals to 250 is actually three standard deviations. Okay, the value 250 is just three standard deviations away or above the mean of 100, and that is what you clearly see in this situation as we find ourselves. Okay, so how do we compare the value of x and then the value of z? Number one, both are standard, both are normal distributions, right? But one of them is standardized. It has been recalibrated to possess a mean of 0 and then a standard deviation of 1. Okay, so in a situation where this question x was normally distributed with a mean of 100 and a standard deviation of 50, we now have a mean, okay, a standardized distribution that has a mean of 0 and then a standard deviation of 1, okay, and given that the position of x is equal to 250, is actually the same as the position of z equals to 3. The distribution is the same. The only thing that has changed are the scale, the parameters that we are using. Okay, you can either express the problem in the original units of x or in standardized units of z. Now, I am very happy that when I mentioned integration, nobody actually got scared. I don't know the kind of impressions that you are having at the other end. The good news about some of these things is that I'm not able to see your faces to determine how you are feeling, or the remarks and the perceptions that you are having. But I can see some indications also from the charts. Okay, so it's okay. As you can see here, the relation is a bit complex, and integrating this kind of expression is quite a tedious job. Okay, so as far as this course is concerned, and as far as many probability theory courses are concerned, when it comes to normal distribution, we hardly use this relation to do it. We actually resort to what we call standard normal distribution tables. Okay, and it is a special kind of table where all the probabilities that we need have been calculated for us. Okay, And basically, you can't do it for all the normal distributions that we know, right? Because we have separate means and separate standard deviations and all that. That is why it is key for us to standardize the normal distribution so that when we are solving, we can easily read from the standard normal distribution tables. So we are going to take some time, okay, and go through um, the process of calculating probabilities from the standard normal distribution table. And most of the things that we are going to do today, tomorrow, and beyond, okay, would be in relation to the standard normal distribution. And I am really hoping and I believe that most of you have downloaded or have um, had a copy of these standard normal distribution tables. You would have to help me. I would pause for a minute and then I would also get my standard normal distribution table ready so that we can all go and work together as to how some of these calculations are to be done using the standard normal distribution. We continue. All right, thank you. So basically, as I was saying, I now have my normal distribution tables and we can easily calculate some of the probabilities that surround the normal distribution. Okay, so normal distribution table looks like this. Okay, as you can see, and mostly it calculates the probabilities from the left of z. We would do more examples and then you would understand what we are saying. Okay, so entries in this table give the area to the curve of the left of the z value. So you see, it determines the shaded portion, and it helps us in calculating. So for example, for z probability that z is for z equal to, let's say, 0.85, right? The cumulative probability, or z less than or equal to 0.85, the cumulative probability is what we would identify from the normal distribution table. And I'll show you how to read from such a distribution table, and then we would move on. Okay. All right. So how do we calculate such probabilities? Okay. It is important to always draw the normal distribution curve so that you would know what is really happening. Okay, so that you know what is really happening, and it is important that we do that. Okay, so let's take some examples of such situations, and then we'll be able to help each other out, right? Okay, great. We have probability. Let's say that x is normally distributed, okay, and we've found the z, and we are looking out for the probability that z is actually less than or equal to, say, 2. Okay, we are looking for this. We are looking out for this probability. Um, what we would do first of all is to draw the normal distribution curve, okay, and identify the area that corresponds to this probability distribution. So what we are going to do is basically we have this value, we have that. Okay, and we already know that for a standard normal distribution, the middle portion is always 0, right? The mean is 0 and the standard deviation is 1. Now, I want us to be interactive, although most of us are not. I mean, we are not here. Okay, so I would want someone to volunteer so that the person will be working with me and we'll be talking together as we move on. If you would like to do that, please let me indicate with a hand up so that we can at least move together and then talk. Okay. Okay, Maureen, very good. Let's go. So Maureen, you can unmute and then we move along. Okay, so we have this, isn't it? Now, if 0 is in the middle, okay, of the distribution, where do you think the value of 2 would lie? Would it lie to the left of 0 or it will lie to the right of 0?
To the right.
To the right of 0. That means 2 will be somewhere here, isn't it?
Yes.
Very good. Now, we are looking for the probability that z is less or equal to 2, isn't it? So how do we find such an area? Does the area occur at the left of 2 or the area would occur at the right of 2?
So less than or equal to 2 means it will occur at the left side.
At the left side. So
yes.
how do I shade that such a portion?
Okay, so it would look something like from where the 2 is, you draw a line to the top,
Right.
and then you shade to your left.
And then I will move to the left, isn't it?
Yeah.
This portion. Right to go further. Or I should end here.
No, I think we can go further because less than or equal to 2 can include values below 0.
Exactly. So less than or equal to 2 is all values that are less than 2. So right from negative infinity up to 2. You get it?
Yeah.
So it includes all of these values. And then we have that moving along. Okay. All right. So it is not in between 0 and 2. Remember, the z is actually one that moves from negative infinity to positive infinity. Remember, we mentioned that. So it's not like your typical binomial or Poisson distribution. Okay, so if it is z less than or equal to 2, it's actually from negative infinity up to positive infinity. Okay, thank you very much, Maureen. Let's take another volunteer to help us with what we are supposed to do. Let's calculate another one. Let's say that we want to calculate the probability that z, and let's say 1 minus 1 less than or equal to z less than or equal to, let's say, 2. Right. How do we indicate this in the curve? Any volunteer to help us if your hand is up? Anyone to help us? Okay, Albert, very good.
Okay.
All right. So let me use curve, right? The curve that we so just hold on. Let me take we have something like this. Yeah, sorry, the drawing went a bit back. So 0 is in the middle, right? Where do you locate the next one and the 2?
Yes, please.
Yeah, so yeah, please walk us through. Okay. I don't think we can hear you so well. So Phil, your hand was up. I would want you to take over. Yeah, Phil.
Okay, sir.
Yeah, let's move. So where is the position of -1 and where is the position of 2?
So please, 2 would be at the right hand side of 0, and -1 would be at the left hand side of 0.
Yeah, right. And then -1 will be somewhere here, right? So
Yes, sir.
how will the shaded portion be? Which areas
Oh.
are we actually evaluating as far as this
With the shaded portion, the boundaries would be -1 and 2. So then you can shade anywhere in between -1 and 2.
all the areas between -1 and 2 will be inclusive, right? We
Yes,
can't
sir.
do becomes 2, and then we can okay. I think that is good. That is perfect. So one of the basic and then the foremost steps. All right, thank you, Phil. Steps in doing some of these probabilities is your ability to shade. Okay, it's your ability to shade and to identify the area where the curve is being evaluated. Okay, so there are lots more to do. Now, there's a problem. Okay, if you look at the table and if you look at the tables that you have, you see the table is able to give you to evaluate probabilities that are lying to the left of the distribution. Okay, so what it means is that when you have the table, we can only evaluate probabilities that are less than or equal to. Okay, somebody's hand is up. Yeah, you have a question?
Yeah, good morning.
Yep.
Please, can you please go back to the probability that z is less than or equal to 2? I want to ask you something.
This?
No, the green one, the one with the green.
Oh, the one I just cleaned. Mhm.
Yes. So I understand that you said we should shade where the negative values are as well.
Yeah.
But if we're looking for probability and it's not supposed to be negative, why should we shade that side?
I understand what you're saying. The probability score, okay, can never be zero. Can never be negative. Okay. Yes, don't mute. So
Okay.
that the range of values of x can be negative or positive. Okay. Here we are looking at what is the probability that z is 2. And z can assume any number from -infinity up to 2. But is the probability, the resulting probability that we calculate, that cannot be a negative number. Okay, but the values of the random variable can assume any number. Okay, it can assume any number between -infinity and +infinity as far as the normal distribution is concerned. For Bernal and Poisson, the random variable could assume only positive integers, that is from 0 till n, or n for binomial, and then 0 to infinity for Poisson. But for a normal distribution, the random variable can assume any value from -infinity to +infinity.
So please, the green part, the shaded portion is representing the random variables, not the probability.
The shaded portion is representing the area, okay, that is occupied by the random variable that we are trying to solve. And that area is the probability, okay? So that is what we are going to calculate, okay? And that area that we will end up calculating cannot be a negative figure. I hope that is okay.
Yes, please. Thank you.
All right, so let's move on. So I was saying something, right? What I was saying was that when you look at the curve very well, you see that the curve evaluates points that are to the left of z. Okay, the curve evaluates points that are to the left of z. So if we have other different probabilities. If you have the areas that are evaluated to the right of z or that are in between certain figures, how do we navigate that? Okay, and that is what I want us to go through. So for instance, assuming you have the probability that z is lying between a and then b, okay, then what it means is that you first evaluate the normal distribution curve at B at point B. Okay, that is probability that Z is less or equal to B. If I'm evaluating probability that Z is less or equal to B, I will take the from negative infinity until you get to B. Then I also evaluate the probability of Z is less or equal to A. That means I'll take from negative infinity up to A. Then when you take the difference, you'll be able to find the resultant value is the probability that Z lies between A and B. Okay, so if you're looking for the boundaries are 2 and you want the probability that Z is less than is lying between A and B, then you have to evaluate at point A, evaluate at point B, and then you would put them together. That is basically what we are saying. There are a lot more examples that we will be looking at, and then you would follow suit as we move on. So, what are the general steps of finding a probability or finding probabilities using the standard normal distribution table? Number one, you have to draw, of course, you have to standardize, right? So you can either standardize before you draw or you draw before you standardize, okay? But either ways, when you translate from X into Z, you draw the normal distribution curve and then you calculate the probabilities using the standard distribution table. It's so simple. Life couldn't be so easier, okay? So that is basically what we are going to use as far as the standard deviations and the means are concerned. Let's take an example and then we'll see what we are supposed to do here. Okay. All right, great. Suppose X is normally distributed with a mean of 8 and a standard deviation of 5. We want to find the probability that X lies between 8 and then 8.6. X is normally distributed with a mean of with a mean of 8 and a standard deviation of 5. You want to find the probability that X lies between 8 and then 8.6. So the first step that you want to go through is to standardize, okay? How do we standardize? We said that in standardizing, we say Z is equal to X minus mu, right? And all of this is divided by sigma, right? X minus mu divided by the standard deviation. This is how we standardize. Okay, so given this, we have to standardize these two values of X. So we standardize the one on the left, and also standardize the one on the right. So let's take Z1. What is mu? Mu is equal to 8. Mu is what? Mu is 8, yeah, that's correct. Mu is 8, sigma is 5, isn't it? Okay. I think someone can also help me as we go through this. Who would volunteer to walk us through this solution? I think that would be better so that you, at least if one student is following and is moving us along, that would be cool. So anybody, hands up, anybody. Okay, Maureen. All right. All right. So the next thing is for us to standardize, isn't it? So let's say standardizing. So what do you have?
The value of X is not there.
Sorry?
The value of X.
Remember that this is the required probability.
Mm.
We are supposed to find the probability that 8 less or equal to X less or equal to what?
8.6.
Right. So we first have to standardize the parts where
Yeah.
we 8, right? And then standardize the parts where we have 8.6. Okay.
Yeah.
So how do you standardize the part where we have 8?
So it will be 8 minus the mu, which is also 8,
Okay.
divided by the 5.
Over 5. Right. So what do you get?
0.
0. Okay. Then the second part will be
8.6
8
minus the 8
minus what? 8
over 5.
what do you get?
0.12.
0.12. Okay. So what does it mean? What it means is that this required probability that we had, the probability that the x lying between 8 and 8.6 has been translated to the probability using the z. Maureen, can you tell us how this probability has been translated to?
So write 0 less than or equal to the z, and then less than or equal to 0.12.
0.1. Okay. Now let's draw this distribution. Okay. And let's draw this distribution. So I can either draw the x or I can draw the z, but I want us to draw the z. Okay. So we have that. We have that. So I know that 0 is somewhere in the middle here, isn't it?
Yeah.
What do we have?
And the 0.12
So the
will be at the right side.
the right side. So let's say 0.12 will be here. Okay, so wherein lies the area that we are going to evaluate?
So between those two, the 0 and the 0.12.
So between 0
Yeah.
and then 0.12. So this is the area of concern, isn't it?
Yeah.
Area of concern. Now, we checked from the slides, we indicated that if we have z lying between A and B, it's the same as well. Probability that z less or equal to B, right? Minus probability that z less or equal to A, isn't it? So
Yes.
it means that what does it mean? If you can help us.
So it means we can have probability that the z is less than or equal to 0.12 minus probability that the z is less than or equal to 0.
It's less than or equal to 0. Very good. So you have to read these two items from the table. Okay. The probability that z is less or equal to 0.12 and the probability that z is less or equal to 0. Now, this is where all of you pay attention. Maureen, you can still be on online. Don't mute yet. This is how the standard normal distribution table looks like, right? Now, to the top, you see values that are that have been corrected into 2 decimal places, right? And then at the sides down, you see values that have been corrected to only 1 decimal place. Now, these two things work together, okay? Then one of the table has negative numbers and then the other table has positive numbers, okay? I am interested in what the probability that z is less than or equal to what? 0.12, isn't it?
Yeah.
I'm interested in 0.12. So how do we find that value 0.12? Now this is what we do, and I want us to pay attention here. You see that this number here and that number here correspond. Okay. So if I want 0.12, I will 0.12 can be broken down into two parts. 0.12 is the same as what? 0.1, right? Plus what?
Yeah.
0.0.
0.02.
Exactly. So what it means is that I will look for 0.1 at the sides, okay, when I go down. Then I'll look for 0.02 at the top. Where they intersect, okay, is the probability I am interested in. I hope that is okay. So
Yeah.
how do I locate 0.12 here? So this is 0.1, isn't it? And then
Yes.
this is 0.02. Okay. Where do they intersect? They meet here at the
0.54776.
0.54776. So the value, that probability we have will be 0.54776 from the normal distribution tables. And then you're supposed to find the probability that z is less or equal to 0. 0 is like 0.00, right? And
Yes.
0.00 is like 0.0 plus 0.00, isn't it? So you have 0.0 here, and then you have 0.00 here. And what's the probability? It's basically 0.5.
0.5.
So minus 0.5. So what becomes of the final answer?
0.04776.
Okay. All right. So I know there are a lot of hands up. All right, Maureen, thanks. And we can now mute so that I can answer some questions. So yeah, Mami, if you have a question, right? Your hand is up. Yes, you can talk.
Yes, thank you. I wanted to ask why the z is not greater than or equal to 0, but is less than or equal to 0.
Why is the z not greater than or equal to 0, but it's less than or equal to 0? We are trying to evaluate using the table, okay? And the table design is such that you can only evaluate from the left. I mean, we have some specialized table that can evaluate from the right. Okay, so the table evaluates from the left. If you can see this, I think I showed them to you. You see, it evaluates only those that are to the left of z. Okay, so if I want a number, the value that lies between 0 and 0.12, and I want to be able to use the table, what happens is that it means that if I'm not interested in probability that z is less than or equal to 0, neither am I interested in the probability that z is less than or equal to 0.12. I am interested in the probability that z lies between 0 and 0.12. But how do we navigate? Okay, we are saying that in order to go through this, evaluate from negative infinity up to the point 0. Okay, then evaluate from negative infinity up to the point 0.12. Then subtract. When you subtract, you're going to get the value that lies between 0 and 0.12. Basically, that is what we are saying. Okay, so that is why we are using the probability that z is less or equal to 0. Is that okay?
Yes, that's okay. Thank you.
Okay, Eugenia, your hand is up. Do you have a question?
Sir, please answer. There was a second question that you asked.
Okay, all right, that's great. Jane, all right.
Thank you. Sir, please, the probability that z is less than or equal to 0.12. When we use the table, we had the value as 0.54776.
Mhm.
But then does it mean that we don't consider the less than sign? Is it treated as equal to?
Yeah, okay, so for continuous distribution, whether strictly less than or less than or equal to, doesn't matter.
Could you please come again?
For continuous distribution, whether strictly less than or equal, it doesn't matter. They are the same. They are treated as the same. It is only for discrete distribution that strictly less than is different from less than or equal to. Is that okay?
Okay, thank you. Yes.
Lawrence, you have a question?
Hello, sir. Hello.
Yeah, I can hear you.
Okay, sir, please. So assuming we are drawing or we are considering the x values, not the z, does that mean that the zero represents the 8?
The 0 represents the 8 because that's the mean, isn't it? Yeah, you can say that.
Okay, and then the 0.122 represents the 8.6.
But you see, for us to be able to use this standard normal distribution to find the probabilities, okay, for us to be able to use the table to find the probabilities, we have to actually standardize them, okay, so that life becomes easier. Otherwise, you have to resort to the integration, which is not a friendly approach. I hope you understand.
Okay, so sir, per what you said earlier,
Right.
can we say that always the mean for z will be 0?
Always what?
The mean for the z, the one in the middle, the 0, will it always be 0 or it will change?
When you standardize, the mean is 0. It is when you standardize that you get a mean of 0 and a standard deviation of 1. Okay.
Okay.
Enoch. 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 Yeah. Can you speak a bit loud so we can hear you?
Yeah. Okay. Thank you, sir. Please, I wanted to know why it subtracted the 0.5 from the probability, where it intersects.
Oh, I think we've already answered this. What I was saying was that because I was looking for figures that lie between 0 and then 0.12, I have to evaluate the probability up to 0, which gave us 0.5. Okay, then I have to evaluate that up to 0.12 and take the difference. So that's this probability was 0.54776. That corresponds to this, and then the 0.5 corresponds to the fact that z is less or equal to 0. I think that's what we said.
Okay.
Eunice.
Thank you very much.
Eunice.
Yeah. Hello, sir. Please, can you hear me?
Yes, I can hear you.
All right. Sir, please, you said with the symmetric something, the left side should be equal to the right.
I said the area occupying the left is the same as the area occupied by the right side. Yeah.
All right, sure. So, sir, please, with the z for 0.12. Yeah, we said it's 0.54776. But when you are taking it from the negative side only, it's not the same. It's 0.4 something something. Yeah. But when I subtract one from, when I do it, one take away 0.54776, I get the negative one.
You would, so, I would explain that. Just follow closely. You will see what is really happening when it comes to symmetric distributions. Okay, but I want you to be online. I want you to help me to work out the remaining questions. So don't mute. Okay, let me just listen to Enoch. I'll come back to you. Eunice, okay?
Yes, please.
All right. Enoch, yes, do you have a question again? Or your hand was still up?
Oh, so the previous one.
Oh, the previous one, right?
Please, can you show the table again?
Okay, this, all right. Can you be a bit, can you speak up a bit?
It's okay, thank you. I can.
All right, okay. So, Eunice, just walk with me. So, Eunice, I want us to calculate this probability. And we are going to use the table, okay? Probability that z is is less or equal to 1.56. First of all, I want us to draw the area that corresponds to the curve, and then we calculate such a probability. Can we do it together?
Yes, please.
All right. Okay. So let's draw the area first. Okay. This is what we have. Okay. I know that it's a standard normal distribution. Sorry. So zero is in the middle. Okay. Where would the 1.56 lie?
You said it's less or equal to
1.56.
1.56. At the right side, please.
Okay, so 1.56 is somewhere here, right? Okay, but what is the area of interest?
Please, we shade all the way from the left to 1.56.
All the way from the left to 1.56. Okay, that is great. So all of these parts, right? So now let's go to the table and calculate. How do we calculate such a probability from the table?
1.56. So is it 1.5? So we'll take 1.5, then 0.6. So we'll trace from 1.5 to the 0.6.
0.06.
Yes, please, 0.06. Sorry.
So you trace from 1.5, right?
Yes, please. Yes, please.
0.06. So there's the value.
So yes, please. 0.94062.
Very good. So we have 0.962. Now, Eunice, I want you to tell me how it's going to play out if we had a. Now we want to do probability that z is less than negative 1.56.
Negative 1.56.
1.56, yeah. So my 0 is still here. Where would the negative 1.56 lie, first of all?
At the left side, please.
At the left side, so somewhere
yes,
here, right? Minus 1.56, isn't it?
Yes, please.
Now, how do we shape? Where do we shape? Let's
the very tail to the left to negative 1.56.
So the very tail, I like that expression. The very tail to the left of, so you get to negative 1.56, isn't it?
Yes, please.
Now, do you realize that compare this table, okay, this curve, to the first one? You saw that the first one occupied a bigger size.
Yes, please.
And this one is occupying a very small area, right?
Yes, please.
There's no way that those probabilities would be the same, isn't it? But if you consider the area to the right of 1.56 and you subtract it from 1, you would assume that those areas are the same. But for now, let's go and read this probability on the table. So where do we locate minus 1.56 on this table?
Minus 1.56. Then we treat it to 0.06.
Minus 1.5 is here. 0. So let me just zoom out a bit. Okay. So we trace it down to 0.06. What do we get? Minus 1.
I can see.
Oh, sorry. Very good. So what do you see?
Surface, I still can see. Okay. I'm kind of straining my eyes. Is it 0.28774?
No.
I can't really see. So
So this
okay, is that 0.05938?
That's great. 0.0. What was the value?
0.05938.
Okay. So basically that is it. Eunice, one more thing. Now let's do this. The probability that z is greater or equal to 1.56. Right. From the curve, where will it lie?
Right side, please.
On the right side. Okay. So we have, so that's 0 here. You still have a 1.56 here, right?
Yes.
Sorry about how I grew my 5. Okay, but where would the shaded portion now lie?
From the right tail end to 1.56.
So from here, like this, like that, and so on and so forth, isn't it? Very good.
Yes, sir.
So how do we calculate such a probability? Now we have a problem. The problem is that what we see from this table, okay, is actually values from the left. But now we are interested in the area to the right. So how do we calculate such a probability? Eunice.
Um, so if you're interested in the value at the left
At the right.
or at the right side,
We're interested in the shaded portion at the right, right? But the table evaluates areas to the left. So how do we?
left, and okay, so I think we can subtract it from 1. We can, when we get the bigger side, the value at the bigger side, the one that reads right from the left to a part of the right, then we subtract it from 1.
Exactly. So probability that z less than 1.5 is 1 minus probability that z is actually less than, probability that z is greater than or equal to 1.56. This is not 1 minus probability that z is less than 1.56, right? And we can evaluate this from the table, isn't it? So I think we got the 0.94, right? So
yes, please.
Only 1 minus 0.9406. What do you get?
We get 0.05938.
938. So you see that area that was occupied by the negative to the left of the negative figure is the same as the area that was occupied to the right of the negative figure. That is how the symmetric properties are like they
operate.
Yes, exactly. They operate. So kind of that thing, and you see that thing happening in here. Once you're able to get the way it works, you can even close your eyes and solve any normal distribution question that you know. All right, Eunice.
All right, sir, please, one question, last one. All right, so sir, please, when I'm to find the bigger portion, I mean the shaded portion, can I just go to the negative distribution table and choose and forget and ignore the negative, rather than me taking the whole figure and subtracting it and doing it 1 minus that whole figure? Can I just go to the negative table and pick it and ignore the negative sign?
When you become very conversant with the normal distribution and how the probabilities work, there are a lot of tips and tricks that you can use to find the probabilities that you're looking for. But as far as let's take this as a starting point, right? So
all right, yes, please.
Then as you solve more questions, you see that there are several ways that you can solve this problem and you can navigate through using the tables. I think that would be fine. Okay. All right.
Yes, please.
Thank you so much. You can meet you now. Jeff, yes, do you have a question?
So my question is, when we began with the using of the table, we began with positive values. So we saw when we're breaking down the decimals, we broke the decimals from I think 1.0 and then 0.56. So we did that tracing and we went to the value that the standard deviation table gives us. And then we went ahead to do negative decimals. That was, I think, what we did before where we are currently. And then we went to the standard deviation table, and then we went to pick a decimal portion that was on the left side, the vertical left side, and then that was decimal. And then we went to take the one above the horizontal, and it was also decimal. But then when we broke down the positive values, we could see that when we add them back, we get it. We get what where we broke down first. But then when we went to the negative values, when we take the negative, for example, we took the negative 1.5, and then we went to take positive 0.06. And in essence, if you add that, you don't get negative 1.5.
I don't get what you're saying, but if I get you right, you are wondering why the probability that z less or equal to 1.56 is giving us a different value than z less or equal to positive 1.56. I don't know if that
No, sir. My worry is just directly towards the breaking down of the decimals to get the corresponding value on the table, because it's just that when we're going to take the positive value, for instance, it was, I think, okay, let's just use 1.56 and it is positive. So he told us that when we are going to the table, when we have a value like 1.56, we can break it down as in 1.5 and then 0.06. Am I right, sir?
That's right. So that's what we did.
Yes, please. Yes, please. So we did that with the positive values. And then we can see that if we add 1.5 plus 0.06, we get back our 1.56. Exactly. Am I on track, sir?
Yes. But
yes. So
I get what you're saying now. When you add negative 1.5 to 0.06, you don't get 1.5.
Yes. You wouldn't get 1.
Like
negative 1.
What I'm typing. Okay. Negative 1.5 plus 0.06. Sorry, 0.5 plus 0.06. So, do you see what I've written?
Yes, please.
Yeah, that's how you should treat it.
Okay, so we have to treat it in a way that the 0.06 at the vertical top is also in negatives.
Exactly. Yeah.
Okay. So is that how the standard deviation table is? Because there's no indication that the vertical top values are in negative.
Yeah. I mean, if you are dealing with the negative side, that is how you should be thinking. Okay,
so we would always have to assume that.
Not assume, I mean, yeah, maybe you have to think that way, that it is actually this kind of operation you are performing. Okay, you just need a 1.5 and you need a 0.06 to get the corresponding values.
Okay, sir. Thank you very much for the clarity.
Just to bring some understanding as to why we are breaking it into two and why we are taking some from the top and taking some from the sides. Okay, but basically, if I arrange it in a way, it will be easier for anybody to pick the values and then calculate the probabilities.
Okay, sir. Right.
Okay. Yeah, I think we've had quite a lot of questions. Let's move on. Our time is almost up. Now we can do more examples, isn't it? We can do more examples. So let's go straight to some of the examples you want to, very practical examples. And since Jeff was the one who asked the last question, I will ask him to volunteer. So Jeff, please you volunteer and then you lead us. Okay. Yeah.
Okay. A warehouse distributor of carpet keeps 6,000 yards of deluxe sharp carpet in stock during a month. The average demand for carpet from the stores that purchase from the distributor is 4,500 yards per month, with a standard deviation of 900 yards. What is the probability that a customer's order will not be met during a month? Assume carpet demand is normally distributed.
Okay. So, what do you think? We have a carpet, a warehouse distributor, right? He keeps 1,000 yards of carpet every time. Okay. And that's what he keeps in his warehouse. So his inventory is 6,000. Now, average demand is normally distributed. We have a mean of 4,500 and then we have a standard deviation of 900. The question is, what's the probability that a customer's order will not be met during a given month? So my question is this: here you've not been asked to find any. It's like the question is not straightforward. Let me just put it simply, right? So how do we bring out the needed information that we want to do? What do you think should be the required probability? Let me say that let x be the demand for the month, right? So we want to find the probability that customer demand will not be met, right? So what would occur to warrant the situation where we will not meet the customer's demand? Yes, Jeff.
I think it will be 1 minus x.
No, forget about the mathematics. Look at the story. What would cause us not to meet our demand? Forget about normal distribution. Look at the story. You keep 6,000 yards in stock, okay? And that your order, somebody's order will not be met. What will cause somebody's order not to be met, given this information? Don't think fast. The answer is right here. Okay, let somebody help you. Okay, someone who has, but you still be online. Okay, Emmanuel.
Yes, please. I think that will happen if the demand exceeds the 6,000 that the warehouse keeps at the time.
The demand exceeds the
6,000.
Okay, Harriet, what do you think also?
I think if you produce less than the average demand of 4,500.
If you produce less than the average demand of 4,500, and Ima said if the demand is more than what you are bringing, right? Ima, is that what you said?
Yes, please. If it exceeds the 6,000.
Yeah. So let's look at these two situations. I always keep 6,000 in my inventory. As for the average demand, it is based on calculations that with historical data. Okay. If in the coming month demand will not be met, that means that in the coming month I am getting orders for more than 6,000 yards. Okay. So Jeff, you have 6,000. Okay. If somebody comes to buy 8,000, can you meet the person's order?
No, sir.
If somebody comes to buy 5,000, can you meet the person's order?
Yes, sir.
Someone comes to buy 6,000. Can you meet the person's order?
Yes, sir.
Exactly. So if somebody buys anything more than 6,000, what you have in inventory, you cannot meet the person's order. You
Yes,
get.
sir.
So the probability that the customer demand will not be met is what the probability that the order, right, or the demand, okay, is what more than what 6,000, right?
Okay. Yes, sir. Yes, sir.
In other words, you are looking for the probability that what x is what greater than what 6,000. I hope that is okay. Is that okay?
Yes, sir.
So my point is that you have to be able to look at the story, look at what is going on, and then try as much as possible to calculate the probability. Even find the required probability before you even try to standardize and find the x and the y minus x and all that. Understanding the question is a basic necessity in getting to even solve the problem. Okay. Now that we have this, we can standardize, right? Jeff, can we standardize?
Yes, sir.
Okay.
Yes, sir, we can.
Z is equal to what? X minus mu divided by sigma, right? What is mu? The mean is what? 4,500, right?
Yes, sir.
Sigma is what? What's the standard deviation?
900, sir.
900. Very good. So 900. So Z is equal to the x you are looking for here is 6,000, right? Minus
4,500 or over 900.
you get. How do you get? Okay. Right. We can just correct it into two decimal places and just write 1.67, isn't it? I think that is. Okay, so when we are drawing with this in mind. So let's see, we have our 0. Sorry, I'm leading you because of the time. Okay, so we have the 0 here. The 1.67 can be oh, sorry. The 1.67 will be to the right of 0, right, Jeff?
Yes, sir.
So 1.67 here. But we are interested in, so basically, we're interested in probability that Z is greater than 1.67. Do you see that? So where will be the shaded portion, the shaded area?
The shaded area will be from 1.67 to the right.
The right. Very, very good. So what it means is that this probability is the same as probability that Z is actually greater.
Which will equal to
what that will not mean, so greater than, strictly greater than, right? Strictly.
Oh, okay, yes, sir.
So how do we read this from the statistical table? Remember that statistical table reads from the left of Z, but we are getting to the right of Z. So what do we do?
Come again, sir.
The statistical table reads from the left of Z, right? But we are now looking for areas to the right of Z. So how do we read this?
We do we first take 1.00.
No, we have to come again. We are doing 1.6.
Okay, we first take 1.6, sorry.
1.6.
Yes, please. And then 0.07. That's 0.95254.
Then what is that the final answer?
Yes, sir.
Okay, so what I was saying was that what you have given, okay, is actually this unshaded portion. Do you get it? But
Yes, sir.
if you are looking for the shaded portion, then it's actually this value, 1 minus.
Yes, sir. So we have to divide it, subtract it from 1.
So 0.95254. What's the resulting value? So 0.047 something. I think you can 4746, right? So basically that is the probability that the person's order will not be met. Okay, so the other questions that you guys can take note of, and I think the time is up. If there are no other questions, we can call it a day. Okay, so any questions? Any questions? Okay, yes, Eugenia.
Sir, please, I wanted to ask, so does it mean that the probability of Z greater than 1.67 is the same as the probability of Z less than negative 1.67?
Yeah, it is. It is. When you draw the curve, you will see that they occupy the same area. Yeah.
Okay, thank you, sir.
That's why I was saying that, you see, the more you become familiar with the distribution and how the probabilities are calculated, you will see how well to navigate a lot of things and situations like that. Okay, so thank you so much for joining. I think that